applications जो है ना, see, whenever the antenna design will be in comply with the applications. Okay. तो फॉर एग्जाम्पल इनिशियली सी अरे क्यों जाता है, पहले अरे क्यों जाते है ये जानना चाहिए, ठीक है। सिंगल एलिमेंट में भी काम हो जाता था, अरे क्यों जाता है ये एक चीज पता होना चाहिए। फॉर एग्जाम्पल सी एफएम टावर्स होते हैं ना, एफएम टावर्स, ठीक
हाँ
है। उसमें तो एक और दो एंटेना रहते हैं, ठीक है, दो एंटेना रहता है
हाँ
बस। उसमें क्या करते हैं, हाइट बहुत हाइट में रख के हाई पावर पंप करता है, ताकि वो, और फ्रीक्वेंसी भी एएम एफएम, एएम में रहता है ना, एएम और एफएम ऐसे ही रहता है ना, ताकि
हाँ
वो जो फ्रीक्वेंसी लो फ्रीक्वेंसी है, ताकि वो ज्यादा दूर पहुंच सके, वैसे ही रहता है, ठीक है।
हम्म,
इसलिए वो एक दो एंटेना एलिमेंट यूज कर रहा था। नेक्स्ट जो है ठीक है, नेक्स्ट इनिशियली हमारा कम्युनिकेशन तो वैसे स्टार्ट हुआ था ना, ये एफ एम वैसे स्टार्ट हुआ था। उसके बाद क्या
हाँ
किया, टेलीकम्युनिकेशन आना शुरू कर दिया था, ठीक है। शुरू हो गया तो देखो, वो लो फ्रीक्वेंसी में उन लोगों ने एंटेना को, मतलब लो फ्रीक्वेंसी उन्होंने इम्प्लीमेंट नहीं कर सका, क्योंकि सी एनी डिवाइस, द डायमेंशन ऑफ एनी डिवाइस इज डायरेक्टली प्रोपोर्शनल टू लैम्डा, ठीक है। लैम्डा इज व्हाट, सी बाय एफ, ये कॉन्सेप्ट तो आपको पक्का मालूम होना चाहिए, ठीक है। लैम्डा इज
हाँ
व्हाट, सी बाय
ठीक है।
एफ, ठीक है। सो व्हेन एफ डिक्रीजेस व्हाट हैपेंस, लैम्डा will
इंक्रीज।
increase, correct? Okay.
हाँ
So which means, see, whenever the frequency decreases, then your lambda will increase, decrease, then you cannot, so your board also will be um, uh, where, see, in general, for example, lambda but 2 size or so, whatever it may be, so that way the lambda also, the board size is, where board size or antenna size or anything will be dictated by these lambdas, okay. That's how it works, okay.
हाँ
So that's why, so that therefore what they did is, so lambda is the one deciding the size and everything. So that's why, in telecommunication frequency, they went to little higher frequency, for example, 900 megahertz, like that. Okay, instead of 100 megahertz, they went to 99 megahertz. And also see this 900 megahertz, it's not selected arbitrarily. So they might have done, they could have done some more measurements. For example, see, frequency versus path loss. Okay. Frequency versus path loss. ठीक है। पाथ लॉस कैसे, how do they calculate? They calculate by creating several scenarios. For example, um, several scenarios, like for example, they will do a brick, and then they give a brick and then do the simulations, and then sorry, brick, and then test it, how much it can penetrate, okay. They will use a glass, then they will check how it can penetrate. They will use a rock, sorry, buildings, then they will scenario create a, check the scenario of building, then how they penetrating. So based on that, they will create a waveform like this, okay, something like this. So
हाँ
frequency versus, so wherever, for example, you may get like, sorry, it will be like this, okay. So wherever you are getting less pathless, that frequency only we will take for the communications, basically, okay. And also
हाँ
what power you have to handle, so all link budget based on this one, okay.
हाँ
Okay. So it's 900 megahertz, even 800 megahertz, 700 megahertz, also some CDMA and all they have implemented. So because CDMA has a, don't have to modulate in the CDMA has a 4 division multiplexes, right? It can reach longer distance, and also you can multiple users can be served at a time. So so these frequencies are decided based on this, based on this particular experiment. Usually the New York University, Bell Labs, so those guys, used to do, and then they publish in FCC and everything. That's how the frequency, FCC, defines the frequency range for the telecommunication. Okay.
हाँ
So you have 1800, so many frequencies are there. Therefore, then when you go for the uh, antenna perspective, right? So initially they can use, for example, if you can pump, see how this antenna gain and the antenna size and other things are calculated. So So this is the RF front end system. This is the antenna. This is the RF front end system. This is the RF front end. This is the antenna. Okay. So now how much I can flexibility and EARP. There is one term called EARP, which is fixed. So this EARP, no, EARP is the one that is defined by the FCC that this much power in dBms, for example, 79 dBm for some band, 76 dBm for some band, like that they define. So on the whole, so when it comes out of this antenna, EARP should be this much. That is how they define. Now it's up to you to design RF front end with the high power. Okay, then you can have a use low gain antenna, or RF front end with the low power. You can use high gain antenna. That's how we design. Okay. So for example, if you are using, in a 5 dBi gain antenna, then accordingly you have to, boost the signals in the RF front end. Okay. And if you are using a 21 dBi gain antenna, then that much flexibility we will get in the RF front end. Okay. That is another perspective. So now in telecommunication, no, that's why the single antenna could not able to cater that for that. That's why they went for the array of antennas, antenna element. Even 2G era itself, we have, for example, dipoles will be like this. Here you will have ports. Here you will have so many dipoles, basically an array, because and which has both port resolution 45 plus 45 minus 45, and plus 45 minus 45 means this one. Okay. So two beams you can means plus 45 minus 45 cross potential we can able to achieve, and many more are there. So now so traditional 2G, 3G, 4G until 4G. Now 5G also, 4G also some intelligence we have. Until 3G perfectly, you had only the directional antennas. Okay, we had array antennas which will directly radiate in the particular sector. That's all. Sector will have, for example, you can form with the 3 antennas, 5 antennas, anything. So you have a form like this. This is the sector. In tower, no, you will see 3 poles will be there. This will cover 120 degree, approximately 120 degree. This will cover 100. Total 360 degree I can able to cover. But in this edge, you will have a problem, because antenna can be, for example, plus minus 45 or plus minus 60, like that. Okay. So they were using the directional antennas like this. Okay. Directional antennas like this. So here there is no beamforming involved. Nothing is involved. Only tilting is involved. Okay. Tilt means this they can be done manually, mechanically, or electrically also you can do it. So how do you do mechanically? So you can just press there will be a passive phase shifters will be there. So when you move, for example, see there will be a feed network like this. When you move this one upwards up, it will excite something. When you move down, it will excite something. That's how the design will be. Okay. See, for example, patch. This is the patch. Okay. This is the patch. Okay. This is the one. So you have feed network something like this. Okay. If you excite at this point, you will get some phase. If you excite at this point, you will get at some phase. Therefore, what you are doing, tilting means, see, this is the tower. You have a tower antenna. You need to cover. See, you cannot see. You can give a mechanical tilt like this, so that it will cover this area basically. Okay. If you beyond that certain range, you cannot able to give a mechanical tilt also. That point of time, you can use the electrical tilt, so that I can cover this area as well. Okay. What it does is it will steer the beam towards the down or up, what depends upon the tilt that you are giving. For example, 2 degree tilt, 5 degree tilt. Okay. So this was done, this mechanism, right? You can just go and manually you increase, insert this. There will be a knob will be there. You can increase or decrease whatever you do. There will be a number. You can do it. Okay. So that the smartness, in 3G they have come up with some smartness. For example, remote electrical tilt unit, which is compliant with the AISG. Okay, antenna interface standard group. Okay. So they came up with this ASD.1.0, 2.0, 3.0. Now we are in 3.0. Okay. What did it is? See, you will have a stepper motor kind of one equipment that will be connected to the base station, and then you can from the NOC network optimization center you can just define tilt number 2. It will stepper motor will just rotate this and then push that up and down. Okay, that's how the 2G or 3G era was working. So in 4G, 4G or 5G, what they wanted to do is, see, There are two things for the phased arrays. Okay. So
Uh,
arrays, they wanted to go see arrays they have been using till in 2G also, but in a different fashion. But in 4G they wanted to make it smart. So what they did is, see, the array concept is not new. It has been there since 1940, the Second World War itself, during Second World War or something like that. After Second World War, because the Second World War they were using the reflectors basically. So
okay.
why we go for an array? Why we go for an array? There are one reason is, for example, see, why we go for an array to give a large coverage. Okay. Earlier, how it was being done using reflectors, parabolic reflectors. Okay. Then they
Uh,
came up with lens as well, lens, dielectric lens, and other things. Okay. So parabolic reflector, how would enhance the gain? You will have a feed, you are having this, it will do the correction, and then so that you can get the longer distance. That's how you could have studied in your paper. So this lens reflector, no. Initially, it was a fixed reflector. Later, reconfigured reflector also came into picture. By using multiple feed, I can able to control the beam in the different direction. Okay, and you can also control the feed, control by controlling the tweaking, tuning the feed. We can able to achieve the steering as well. Okay, but it was a bit difficult basically. Then they came up with the array concept. So they wanted to have a flat surface and it can be embedded in the different system or satellite or anything. So they came up with the phased array concept, which is a printed elements basically. It can be phased array, can be C. It need not be printed elements. It can be a dipole arrays. It can be a reflector arrays also. Multiple reflector placed in a different direction by exciting different phase and amplitude. You can able to control the beams. Okay. So this is the array. In general, array means array element can be anything. Okay. In general, array
uh,
means array element can be anything. It can be a phased array. It can be a reflector. It can be a you know. Can be a reflector, it can be a phased array, sorry, it can be reflector, it can be a dipole, it can be a lens or anything. It can be a printed elements also. So now coming back to this concept was there in the defense system. Okay, they can, for example, see you have a radar system like this. Okay? You have flight enemy and target, enemy fighter jet is going on like this. I want to track that fighter jet where it is going, okay, from where it is coming. So what it does is, say, there will be a bistatic radar, two static, single static radar like that. There are multiple approaches. Is that okay? So bistatic scattering method. So how it does is, it will send a signal based on the reflection. It will find out, okay, what is the object is, how it will look like, and what speed it is going. You can able to detect. So how you will detect? So based on the reflected signal, no. So you can, yeah, it will be a 3D. It can be initially to start with a 1D location where exactly the target is. So what it does is, see, how you calculate. You will send the signal, and then it will come back. So it will take certain time, right?
uh,
You know that velocity, okay, you know the velocity, right?
uh,
Velocity is what? Distance by time, right?
uh,
Okay,
Done.
okay, time, right? So if you know the velocity, if you know the time, then what I can do? I can able to find out d, right? D
Uh,
is equal to velocity into time. Okay, so I can able to find out what distance it is, and based on the, if you do say direction of arrival, direction of reduction, using that method, you can able to clearly find out what is the object size is, how it will look like, and other stuff. Okay, so, and a second thing is that we can able to steer the beams like this. Okay, for example, simple example is, see, either you can do mechanically or electrically. Okay, in airport and all, you might have seen like this. A linear array will be there, or earlier it was reflected. Now a linear array, yeah, they are using. Just, it will keep on rotating in order to see where is the flight is. Okay, they are steering the beam using mechanical structure.
okay. No.
So, but in every places it cannot be possible. Mechanical steering is not possible. That's why we go for the phased array concept. Okay. As I said, phased array elements can be anything. It can be anything. It can be a reflector. It can be dipole. It can be the lens. It can be printed elements. Anything. Okay. This is it. So what I'm going to do is, see, I have to steer the beam in any direction that I want within certain range, dynamic range.
हाँ.
For example, I can able to steer the beam plus minus 60, plus minus 50, plus minus 45 like that. I should be able to steer the beam. How I can do? I can able to control the phase, amplitude and phase of these signals, and also excitation, amplitude and phase. Okay. So by applying by exciting the appropriate phase and amplitude distribution, I shall able to control the beams that I want. Okay, that's how array theory says, right? Array theory, what it does, you have array factor, then you have element pattern, right? Element pattern. So by control, array factor is defined by this, excitation and everything. You are just to multiply. So this is how the phased array came into picture. So what is the unique use of this? So phased array, why they are using, especially in 5G, why they are using? Because see, there are two purpose. One is coverage enhancement. As I said, you have the sector. This is the let's say this is the coverage area. Okay, okay. So this is the coverage area in the traditional system. Okay, you will see equal power, almost equal power. Okay, not exactly, almost equal power in all the area. So whatever user falls into this, I can able to serve. I cannot serve beyond this range. Okay.
Mm.
Okay, in the traditional system, whether a user there or not within this cell, you do not bother. You keep on transmitting the power. That's it. You are wasting the energy, right? That's why they came up with they came up with a concept called, okay, if you are using high gain antennas like massive MIMO, phased arrays, what you can do is you can steer the beam wherever you want, right? Wherever the user is. So what I will do, instead of, see, there is no user here, but I have user here, plenty of user, which is not getting served. What I will do, I will create a beam like this, another beam like this, and maybe one beam can cover both user also, possible, and another beam like this. I will steer them. Okay. So here what I am doing, I am enhancing my coverage range. That is point number one. Point number one is what? I am enhancing the coverage range. Correct. Okay, point number one. Therefore, I need not put multiple cells, multiple towers in the for the certain area. Correct. Second thing is I'm improving the spectrum efficiency. So whenever there is a user, I will steer the beam. That's it, right? I'm serving the, instead of serving only 3 user, I'm also serving the extra 5 users by employing this one. So therefore, I'm enhancing the user experience as well. User will get a dedicated beam. Therefore, I'm getting the enhanced user capability. Okay. So this is the two advantages. One is enhancing the coverage range. Second is enhancing the user experience, and also the number of cell towers can be reduced. Third thing is that you can use multiple layers, right? So a massive MIMO has multiple beams, multiple layers. Therefore, I can able to enhance the throughput as well. Okay, through multiple beams, I can able to send multiple data streams at a time. So therefore, I can able to achieve the enhanced throughput. Spectral efficiency is being increased. That is another point. Third point is fourth point is like when you are enhancing the gain. For example, if you are having short beam in a short beam like this, so you will roughly have a 24.5 dBi gain like that. Okay. So when you are having this, you can able to in RF antenna, you need not use 40 dBm output power or 46 dBm output for PA and all. So the PA power is getting reduced now. Okay. Therefore, you are you are saving the power right, energy, right, in the RF front end side as well. Okay. When you are using high gain antennas like this, then you are saving the energy in the RF front end side as well. Okay. So these are all the perspective of the phased arrays. Okay. And what else you want to know?
और स्टीयरिंग मतलब यही होता है क्या, जैसे डायरेक्शन?
Yes, exactly. Steering means that one.
और अरे स्कैनिंग क्या होता है?
Beam scanning or beam steering is, in layman language it is same. Okay. Beam scanning and beam steering. Beam scanning means it will scan for the, some signal is coming or not. That is beam scanning. Beam steering also, the one of the processes beam steering. Beam steering means I can steer the beam like this. Okay. I can steer the beam like this. Any direction that I want.
अच्छा.
You cannot able to do, see, you can able to do to certain extent with these 2 or 3 elements, but you need to have plenty of elements, for example, in a 64, 128 or 192
Okay.
to accomplish this. Okay.
Uh-huh.
Any other doubts?